Hey everyone, welcome to our second and final lesson on geometric sequences and series, which we discussed in our last video. And we saw that we have two different types of geometric problems that we're going to be looking at, one of which is like a list of numbers, that would be for a sequence, and the other of which would be for a series. And each of these things have their own different formula that we use in order to solve. So for example, if we wanted to find, let's say, the fifth number in this geometric sequence, we would look for three different variables in accordance with 1, 2, 3 variables in the geometric sequence formula. And that would be the first number, which here would be a 1, and the common ratio, which every geometric sequence and series has. In this case, what do you multiplying by moving forwards through the sequence, or dividing by moving backwards. 1 times 3 is 3, 3 times 3 is 9, 9 times 3. We're always multiplying by a 3 moving forwards and dividing by a 3 backwards, right? 27 divided by 9 is 3. 9 over 3 is 3. 3 over 1. Common ratio here is 3. And if we wanted to look at the fifth term, okay, now in this problem we could see easily that's 81, right? It's the fifth number that shows up. But we could also use this formula, and as we're starting to look at more and more numbers, right? Maybe we want to look at the 20th number. That formula becomes more and more useful because it becomes harder and harder to keep track of how many numbers show up in the sequence. So just to confirm this real quick, first number would be a 1, ratio R is 3, n minus 1, 5 minus 1 turns out to be 1 times 3 to the 4th power. 3 to the 4th power is 81, and anything times 1 stays the same. So 81 does match the fifth term according to this formula, as it should. For a series, on the other hand, where if you're adding up a lot of different numbers, and let's say that we're also going to add up 5 numbers here, yes, you could do that manually. And if you added up all 5 of those numbers manually, that would be 121. That's one way that you could solve this problem. But as we've seen, the more and more numbers that you're expected to add here, right? Let's say that you wanted to add 20 numbers in this series. We can continue on and on listing more and more numbers in the series. It's going to be harder and harder to keep track of how many numbers you're really adding up and finding those numbers in the first place. So instead we use the geometric series formula, which should give us the same answer as we have up there. Again, the nice thing about geometric sequences and series is you're always looking for the same thing. So first number is once again a 1. Common ratio here again is 3. You're still multiplying by 3, just like you were for the sequence. Difference is that you're adding numbers. Okay. And let's say that we want to add 5 numbers. Again, according to this formula, we should end up with a 121, which makes sense, right? This should be bigger than this. The formula that we have over here is just looking at one number. The series formula is looking at adding a bunch of numbers. So we should end up with something bigger than 81, like 121. So in this case, first number is 1. We're going to have 1 minus r to the power of n all over 1 minus r. Put that in parentheses, especially if you're using a handheld calculator. If you wanted to simplify this in a calculator, you could. I'm just going to very quickly go through and simplify this by hand. 1 minus 243 is negative 242. 1 times anything stays the same, and if you divide those, whoops, that should be a 3 down here, excuse me. I was wondering why this was not going to work out. 1 minus 3 in the denominator, so my apologies, that should be a negative 2. And if you divide those two numbers, that will get you to a positive 121. So the formula does work, you just have to make sure you're plugging in the right variables with the right numbers. And the more and more numbers that we add up, or the more and more numbers that we look at in a sequence, the more and more useful these formulas become. Now, what I mentioned in my last video is I actually wanted to show where this geometric series formula comes from, because sometimes in math we tell you things that do work, but we don't exactly show why. We are going to expect you to know the steps in which you can find this geometric series formula. So these are the steps listed here. It's a lot of notation. You will be expected to know how to order these correctly. But I actually want to walk through and explain how you can actually find, with an example, this works. So for example, where does this even come from? Where do we even start when we're looking at a geometric series problem? So I came up with an example listed here where we're adding up a string of numbers, and this is a geometric series, right? We're constantly multiplying by something to get to the next number in the series, and we're multiplying by a 2. 3 times 2 is 6, 6 times 2 is 12, so on and so forth, okay? So I've represented that a little bit differently down here, as you can see, right? The first number is a 3, the second number is 3 times the common ratio, the third number is 3 times the common ratio again, so that's why that's squared there, and then we multiply by the common ratio again, and to get to the next number we do it again, and so on and so forth. What you'll see is that these 8 numbers, if you count them up, there's 8 of them. Okay, these 8 numbers add up to be 765, as do these numbers down here from our geometric sequence. And this shows where step 1 is coming from, right? You have this initial number, right? A, 3, that's your initial number of A. Then you have 3 times R, right? Your common ratio, 3 times 2. And that matches this. And then this matches this, and so on and so forth until you get to the very end. Okay, I don't have enough space to write all of it out, so I kind of skipped a few numbers there, but these match as well. Notice we had 8 numbers in this series, and we ended up with an exponent of 7. Now why that's the case is because 7 of these numbers have a common ratio in them, and then the first number is where you start, so 7 plus 1 would be 8 total numbers. So there should only be 7 numbers that have a common ratio, not 8 numbers that have a common ratio. Okay? So that's where this first step is coming from. And from here, I think the next few steps are pretty clear. So number 1, this is like our beginning. Okay. Number 2, we're reversing, right? And this is no different than saying 1 plus 2 is the same as 2 plus 1. We're just switching whatever's in the back side of the right hand of the problem towards the front, and then A moves towards the back. So A first, then reverse. Then we're going to factor out an A. See, all of these terms here have A in it. Let's factor using the GCF method. Okay, we can take out an A or divide A out of all of these terms on the inside. We're going to multiply both sides by 1 minus R, and this is where you might begin to see the beginnings of where our actual final formula is going to come into play here, right? 1 minus R, we're going to multiply that to both sides. Because after we actually multiply this out, okay, multiply to both sides, then multiply the right-hand side, these two right-hand sides equal each other. Now that might be hard to see, so what I did was went back to my example over here and wondered, okay, where does this step 5, where does this right-hand side come from? And it comes from the fact that if we add up all of these separate numbers that we see here, right? You have A, your initial. 1 minus R would be 1 minus your ratio of 2. And you have these numbers that are popping up in the parentheses, right, where N is 8, because you had 8 terms that you started with in your original problem. And you simplify all of this, and this should be in parentheses here. That'll give you a negative 765, okay? You could check that in the calculator. You'll end up being negative 765, and that's the same as if we take 3, your initial, 1 minus r to the power of n, the same thing, okay? So that's where step 5 comes from step 4. They both are the same. They're equivalent on the right-hand side. And lastly, divide by 1 minus r from the left side to the right. Your series is equal to this formula. So a first reverse, factor out an a, right? Then multiply to both sides by 1 minus r. Simplify would be another word here that you could use for step 5 if you don't want to use the same word as step 4. Simplify step 5 by multiplying this out a little bit and divide. That's the order of the steps in which you take to derive the geometric series formula. Again, that is something that you need to know, so make sure that you can order these steps. I wouldn't expect you to have to list them all out, but you do need to put them in order. If I rearrange them, put them back in order. And the way that you can do that, I think, is by remembering these keywords, okay? Another thing that I wanted to mention before we end the lesson on geometric sequences and series is how you can approach real-world problems. When do you actually use this, right? So let's say you're a doctor and somebody has to take medicine, right? And they're not allowed to take so much medicine at one point, right? Because when you take a tablet of medicine, that stays in your body for a while. So you can't just take all of your tablets at once. That's overdosing, right? You have to space those out. So let's think about a problem in which you have a tablet that contains 100 milligrams of some antibiotic, 15% of which stays in your body by the time you take your next tablet. So maybe that's the next day, maybe that's the next week, okay, whatever. That's another key number there. And let's say that we have 11 tablets total that we're going to take, and then we've finished the medicine, we're cured. Okay. So in this case, A1, your initial, is 100 milligrams. Your ratio, the common ratio here, is going to be 15% because that's always what's left over after you take your tablet. So you start with 100, but then all that's left over when you take the next dose will be 15%. And we're going to change this, as usual, to decimal form by dividing by 100. Okay. And lastly, n. N is going to be 11. The question is, are we going to use the geometric sequence formula or the geometric series formula, right? Are we going to look for just what happens at the 11th tablet, or is there an accumulation effect here? And it turns out we're going to use the series formula, right? You start with 100, yes, but then when you take your next tablet, that's another 100 plus whatever you had left over from the first, right? It's like your first tablet. And then when you take your next tablet, that'll be your third one, you'll have another 100 ingested plus whatever you got from your previous tablet and the first one again. And so on and so forth, okay? This medicine is accumulating in your body. So that means that we're adding, in this case, okay, it's a series, not a sequence. We're using this formula, and that means we're going to take 100 times 1 minus r, so 1 minus 0.15 to the power of 11. Don't forget to put your denominator in parentheses, and again, that's 1 minus r, okay? And if you do calculate this, and I mean, obviously I need a calculator for this as well, I'm not going to be able to do that in my head. You'll end up that the medicine in your body after 11 tablets is 117.65, you'll have to round up, milligrams. Okay, so it's a real world problem. More and more antibiotic accumulates, that's enough for you to be able to have a cured ear infection, which is good. So this is something that you could see if you were to become sort of like a medical doctor in the future. Okay? You have to know how much medicine accumulates over time. Geometric series formula for that one. All right, one more example of a real-world problem, and then that'll wrap things up. Let's take something that can apply to anybody, right? After school or college, let's say that you are looking for a job and you find one, or Leon does anyway, and he starts with a salary, and that salary increases each year, and they agree to increase it by 3.7% every year, annually. Okay. Let's say that Leon earns $72,176 in his 9th year of working at that company. But then he forgets how much he started with, right? And it's useful to keep track of these sorts of things like, oh, you know, where did I start? Where did I end up at, currently? So he wants to think about what his starting salary was. Well, when we're talking about starting salary, we're talking about initial. We're talking about A1. We're looking for that. Now, the question once again is, should we be using the sequence formula or the series formula? In this case, you use the sequence formula, right? Each year his salary increases, but it's not like they add his previous salary. You know, in year 2, they're not taking his first salary and then increasing that and adding that to his second year salary. No. If he saved that money, that's fine, but his second year salary is something completely different than his first year salary. Same with his 9th. His 9th year salary, completely different than his first year salary. It doesn't add it, it just compiles interest upon it. So we're going to use the sequence formula. Think about what that 9th year will look like. And we know all the other information, right? We know what the final salary is going to be. That's the salary in the 9th year. We know what the rate should be. It's 1 plus, and don't forget to turn this into decimal form. Okay, divide that by 100. And we know that n is year 9, so 9 minus 1. The only thing that we don't know is the initial. That's what we're solving for. Okay, this is a solving problem. Now, one thing I want to mention here is that we have to add this by 1. Remember your growth formula problem. Your base can't be less than 1 here. If your salary is increasing, you have to have a number that's higher than 1, not lower than 1. So in this case, that is 1.037. Okay, that's a number bigger than 1. We have to add by 1. Okay, that would stay flat if it was just multiplying by 1. Now we're increasing by 3.7%. 9 minus 1 is 8. And if you divide, right, this to the other side of your problem to solve for A, that is how you would approach finding the first year's salary. So doing that in the calculator, making sure that you're careful that all the numbers are what they should be. In this case, Leon's salary started at, and be careful with rounding here, $53,971.29. You will have to round up, okay, 29 cents. It was 0.285, round that up to 2 decimal places for dollars and cents. That's what he started with. So what we're going to do next, and that was like part 1 of a part 2 problem, we're going to think about if Leon saved all his money, okay, from year 1 to year 9, that's when he's starting to add everything, right? That would be a geometric series problem. He takes his year 1 salary plus year 2 plus year 3. He's saving all that money. Okay. That would be where we're using a geometric series problem. And because we know all the useful information, right? We know his starting salary now. We know the rate, the common ratio. We're multiplying by 3.7%. or 0.037 every year. And we're looking at n equals 9 yet again. That's where we can use the geometric series formula now to see, okay, how much did he potentially save in 9 years? So very quickly, take his initial, multiply that by 1 minus r, again, that's 0.37. Should that be 1 point or is yes, 1 point, excuse me. Remember, we're adding by 1 here, because that's what he increases by. The rate is 1.037, as we saw earlier. We are taking that to the 9th power, okay? N is 9. His salary is increasing, of course, so that should be a number higher than 1. R is bigger than 1. And then 1 minus 1.037 in the denominator as well, wrap that in parentheses, should give you a final answer here. You have to forgive my spacing, but that's $564,195.37. This is a problem where you would round down rather than up. So that is how you can definitely see over time how much money that you could save at a similar type of job, and maybe try to budget or plan accordingly. So hopefully that helped y'all. That wraps up our discussion of geometric sequences and series. We're going to move on into a new subject starting in our next video series on graphing equations and inequalities, and I look to see you then.